So to me, the necessity of closed loop A and B are so important because before you use this closed loop C, you have to have prior knowledge to what type of field distribution you're dealing with. In this case, because the solenoid is so long, the length is infinite, therefore making the inside to having a constant field. Field inside is not position dependent. Field outside is also a constant. Here is having a value, here is having the same value, here the same value. All right? So you have to know these two informations before you can proceed to using closed loop C. Now we turn to closed loop C. Okay. Inside it, we have a constant field amplitude called B. Outside, so we're trying to evaluate these two segments. So here, I know the length is L. So I have a constant field inside. So this is B in times L. Ideally minus B out times L. But usually we just write this one. Why? You would be very surprised. I'm spending so much time on this simple example, which everybody knew it or learned it starting from high school. But as we unveil the reality, probably you realize how much details were being omitted in the past, right? In the past, you just write down this equation. Everybody knew how to write down this equation. But how to justify this equation is correct. And that requires your deep understanding. The reason we can just write BZ times L, this BZ is B inside, B in, right? B in times L, that is your line integration, equals to this quantity. Well, this quantity is direct and straightforward because whenever you have the length L, you know your wire density. N times L in times I tells you how much total current is being encompassed by your closed loop. But the real trick comes from the left-hand side. Why? Because, well, whenever we have a closed loop, if we don't care about these two y-oriented segments, aren't we supposed to also evaluate the path integration of the top segment? But here, it's not visible. So here comes the truth. Well, I mean, refresh your memory. In the past, we romantically just assumed outside of the solenoid, we have no field line. So the flux density is 0, right? TA, is it true? I mean, in the past, all the teachers, all the professors just tell you that. But in fact, using this closed loop, B, in my PowerPoint, we only have the result of B1 equals B2. So it only tells you outside you have a constant field. But no word is telling you it is equal to 0. It is constant everywhere, but who decides it's 0? Can anyone answer that question? From our detailed analysis, field outside should be a constant, not spatially dependent. Field inside, also a constant, point by point, they are the same. But somehow, in the past, it's a custom to say that outside of the solenoid, the B field is 0. And because B field is 0, so you know the B field inside the solenoid, right? Something minus 0 is equal to the total amount of current encompassed. So can anyone tell me, this is a challenge to the students, how can we just romantically say this is 0? Well, if this is not 0, let me tell you the ugly truth. If the field outside, well, it's a constant, right? But if it's not 0, you don't have a way to quantify the field inside. Right? If you use loop C, all you have is B in times L minus B out times L is equal to mu 0 and Li. The ugly truth is, well, if you really use closed loop C to perform the evaluation, this is what you get. You have the field inside the solenoid minus the field outside of solenoid is equal to the total current encompassed. So you still cannot quantify either of the field. The only way you can satisfy yourself and write down a beautiful answer and hoping that you can get score is you say this is 0. And therefore you can quantify. But you have to tell me, I mean, what's the reason behind this beautiful no field outside of the solenoid? I'm getting you to think, right? Finally. So you should watch the video, the streaming. Okay? The problems we're working with are extremely impractical, extremely ideal. So the magic word comes to infinite. Currently, we're assuming the solenoid is infinitely long. Okay? Infinitely long. What does that tell you? And it's a real test to your understanding to how the B field look like. Okay? As I stated, the B fields form a closed loop. So somehow inside the solenoid, the amplitude, the magnitude is a constant, which is fine. I have no objection to that. But somehow when you, well, at a certain point, your solenoid has to end. So basically, your field line forms a closed loop, right? So think about it. This must be true. Inside the solenoid, you have very constant B field. But each field line needs to close upon itself. So if you really draw out the resulting B field lines, how can you say when you're outside, you have no field? Think about it. Can anyone answer? I mean, I have 3 filming crews who are all in the sophomore or junior year. I have the TA who's a master's student. Can the 4 of you answer this question? apparently, what I'm trying to point out is apparently we're doing something wrong. Because apparently, magnetic field lines close upon itself, so each field line you have inside must have the corresponding field line outside. But somehow in our derivation, we just assumed there's no field outside. Under this assumption, we can quantify the field inside. This is really weird. Okay? So anyway, when you're receiving a test problem, okay, not from me, you write down the so-called right answer. But if you are on a test, examination in my class, I'm more than happy to see your challenge to this simple problem. If you can write down all your reasonings, this is wrong, how the answer should be adjusted or modified, I'm more than happy to see your rebuttal. Okay? So what is the secret behind this answer being correct? It has been there for over 100 years. And all the professors just give you the points when he or she sees this answer. So this is the point where you have to understand for each individual problem you're given, you are bounded or you're luckily spared by assumptions. Infinitely long solenoid. So under this assumption, this impractical, perfect assumption, you are allowed to say that there is no field outside the solenoid, even though you know the fact B field lines close upon itself. Why? When the solenoid is extremely long, which also tells you your observation point outside the solenoid is very close to the solenoid. Okay? So this is telling you, well, okay, I have a closed loop B field outside of the solenoid, but compared to the distance. For example, this is Earth, right? The solenoid is the core of the Earth, and we are at the surface, and this field line is somewhere at the sun, right? So the distance between the Earth to the sun is so long. Basically, all the fields are penetrating the sun and not Moon, not Mars, not Earth. And therefore, we say, oh, here, outside, there's no field line. Okay? What I want to show you is, in practice, if you have a finite length of solenoid, don't ever think about using Ampere's circuital law to find the resulting B field strength. Because when your length is finite, as you can see, right? When your length is finite, all the fields close upon themselves. So basically, you do have field immediately outside of the solenoid. So in this case, you form a closed loop. You have to evaluate B inside minus B outside. They're both unknown quantities. So what do you gain? Nothing. So the current case we're trying to analyze is more like this case, right? This case is having a quite uniform B field near the core, and it does close upon itself, but it's so far away. So this field line is not penetrating across this point, right? So the difference between a finite length solenoid and an infinitely long solenoid is when you increase the length of the solenoid, you're trying to remove all these so-called near-field flux densities. So in the far field, when you're very far away, you do have fields. But when you're close to it, you don't have the field lines. And all the field lines are concentrated inside the solenoid. Okay? Now think about it. This is very profound. Because it's very profound, I'm spending 20 minutes to talk about it. Right? So think about the need to form A and B loops. To me, your ability to form the A-B closed loops is a winning key to understanding this simple problem. All right? Actually, if you have a finite length, you form a closed loop inside, you know the B field at this point will be different from this point. Okay? So each problem, I welcome you to challenge the end result, but you have to come up with a proper explanation why you have your challenges. Right? Okay? Oh, by the way, this picture is extremely profound in a way that if you think this problem as a boundary value problem, the B field lines close upon themselves. But if you view this as a boundary, okay, what do I mean by the boundary? Boundary, right? Two different materials forming an interface. So if you have the field line coming in, somehow your output field line is, so this is B inside and this is B outside. I'm trying to attract your attention to this particular closed loop. At the interface, your B field line is coming in with certain angle, and your B out is here with certain angle, but they are both on the same side of the surface normal. Now think about it. This is a very unique capability only seen in magnetic fields. So as your examination is coming up next Monday, everything in E field, you have a field coming in, right? D field, and you have a field coming out, D out. In the world of electricity, the boundary values would always require the input field and the output field are on the different sides of the surface normal. But here in the world of magnetism, well, input field and output field are allowed to be on the same side of the surface normal. This is interesting, weird, and I want to challenge you to finding out why. What is the difference that allows magnetic fields to appear on the same side when you consider a boundary value problem? Okay? And I promise you, the final examination, there will be one problem appearing about this issue. Okay? So this is a real understanding to the difference between E field and magnetic fields. Right? So I propose we stop here. We take an early recess of 10 minutes. So we come back and continue on the next subtopic. All right, so let's take a 10 minutes rest, unless there are students having questions online.